So the question is that 30 random observations are taken from each of the following distributions and the sample mean calculated. For each of the following cases, find the probability that the sample mean exceeds 5. So your first case is X is the number of telephone calls made in an evening for a counseling service where lambda is equals to 4.5 and follows the Poisson distribution. For simplicity's sake, we can consider that the Poisson distribution is our population, but you can also consider it in a way कि एक sample है and you're taking further samples from that one sample. But yeah, again, for simplicity's sake, let's just call this our population distribution basically. And we can make what will be the mean and standard deviation for this. What the question is basically asking is कि I am taking 30 random observations, okay, and these 30 random observations can have a distribution of itself. I can take different combinations of these 30 observations, these 30 random pickings from this population, and what that distribution would be the sampling distribution of sample means basically. So that would be my sampling distribution of sample means. And from that sampling distribution, I'm trying to figure out what would be the probability that I can exceed a 5. I can exceed a mean of 5 in that. When your population is a Poisson distribution, your mean is going to be simply lambda, and your standard deviation is going to be square root lambda. Your sampling distribution of sample means has a mean that is equal to your population mean. So this will simply be equal to this, it will be equal to lambda as well. And your sampling distribution of sampling means has a standard deviation, or what you call a standard error, which is equal to the standard deviation. This could be the standard deviation of the population or the sampling distribution as well. It depends on what has been given to you in the question. In this question, we already have the standard deviation of the population, so we'll use that. Divided by n square root. So the standard deviation of the population is actually square root lambda, so we'll just put this over here. Okay, now I can use the z-score, or I can use the t-table as well, but we'll stick to z-score again for simplicity's sake. Z-score is equals to x, whatever value, basically, which will be 5 over here, whatever value I'm trying to see where it lies on this distribution, x minus the standard deviation, x minus the mean, x minus the mean, obviously, divided by, this is the sampling distribution sample mean, we're calculating this z-score. So x minus lambda divided by your standard deviation or standard error will be lambda over under root n. So if we can assume we've already been given a 4.5 lambda, I just have to plug in values for this. This n is basically the number of observations. This will be 30. So it will be 5 minus lambda is 4.5 divided by, again lambda is 4.5 divided by under root 30. This will come out to be 1.29. This will be the z-score of this distribution. This is where my 5 lies basically. I now need to compute what's the probability of, what is the probability of a value lying below basically above this, because we're doing exceeds 5 basically. So if you have like a distribution and I have gotten the value 1.29, what is asking from me is this area. But when we look at a z-table, we usually get the value, the probability or the area of this curve towards the left. So when I look at 1.29 in the z-table, what I'll get is the area for this part, which will be equal to 0.9015 for this specific value. And I'll just subtract this 1 minus 0.9015 to get the area of this part, which will be 0.0985. Again, because I was trying to look at the probability above having a mean of 5. For this second case, we have x is the number of heads obtained when an unbiased coin is tossed 9 times. We're using absolutely the same idea that we did in part A, except that my population distribution is going to be different in this case. We've already looked at this case. We can model number of heads obtained when an unbiased coin is tossed 9 times using a binomial distribution. So if we are using a binomial distribution, again, why we're using a binomial distribution, you have a fixed amount of P and Q, which is going to be 0.5. You have a fixed number of trials, and you have like a fixed number of trials, which are, let's do n trials, which are 9 in this case. And then you're looking at the number of heads obtained when an unbiased coin is tossed 9 times. So if I had like the value of x, if I had the number of successes that I wanted, I could just plug this into the binomials formula and compute it for that particular case. For this scenario, we have the population, we have the mean and standard deviation. Again, similar, we'll do it the similar way that we did for the last question. Sampling distribution of sample means, again, because we're trying to figure out that I've taken 30 pickings, random pickings from this population, and I'm trying to see what is the probability that my mean will exceed a 5. So sampling distribution of sample means, okay, so when you have a binomial distribution, the mean comes out to be NP, and your standard deviation is square root NPQ. Again, sampling distribution of sample means, the mean for this will be equal to the population mean, NP, and sampling distribution of sample means the standard deviation or the standard error will be equal to, okay, let's call this n trials, because this is going to create a bit of problem aage jaake, because we have 30 of, so we can say n observations is equals to 30, and n trials, the number of times that I've tossed a coin, is 9. So we can call this n trial P, n trial PQ, n trial P. Okay, n trial P. Okay, so your standard deviation for this, the formula for this is the number of observations that you have, and we have the standard deviation of the population or the sample. In this case, again, we have the standard deviation of this population, so I'm going to use the standard deviation of this population to calculate the standard error of the sampling distribution of sample means. The standard deviation of the population is n trials PQ square root, and this is going to be n divided by n square root n observations, okay, which is 30. Again, I am now trying to look at the value of 5, the mean of 5. What will be the probability that would be the area under the graph above this 5 mean for this particular distribution? So we can again calculate the z-score. X minus the mean over here is n trial P divided by this whole thing over here, n trial PQ divided by n observations. You can plug in the values. 5 minus n trial is 9 into 0.5. The P we already established, it's an unbiased coin. N trials again is going to be, n trials is again going to be 9 into 0.5 into 0.5. We already have PQ divided by the number of observations, which is 30. This will come out to be around 1.83. We have to do exactly the same thing that we did in the last example. I'll locate 1.83. I'll look at the z table. I'll find the value for this part of the graph, which is equal to 0.9664, and I have to compute this area, so I'll just minus 1 minus 0.9664 This will come out to be 0.336. So 0.336 is the area above this 1.83 mark, which actually signifies the mean of a mean of 5 for this specific sampling distribution.